Okay, we're going to look at nuclear fission now. So we looked at fusion, which is fusing two nuclei together and releasing energy that way. Fission is the splitting of a nucleus, and again you get a lot of energy out. So the way this is done, the way it was done with the bomb that was dropped on, well, the bombs that were dropped on Hiroshima and Nagasaki in Japan, what would have happened is when the bomb was a certain distance from the ground, a few hundred meters off the ground, a high energy neutron would have been fired into the nucleus of a uranium atom, and it would have split the uranium atom, and more high energy neutrons would have flown off, and they would have collided with more nuclei, and so on and so forth. So here goes our high energy neutron. It hits the nucleus. Now this becomes unstable, and it becomes unstable because a nucleus does not like to have a large imbalance of protons and neutrons. So now it's got an imbalance of protons and neutrons, it becomes unstable and it splits, and you get this massive release of energy. We get two fission products, and we get three more high energy neutrons, and they fly off, and there we go. That's what happens. So we've got a diagram here. There's a high energy neutron, hits the uranium, that splits. Now in this case, the fission products are krypton and barium, and then the three neutrons go off and smash into three other uranium nuclei, and then you get 9 neutrons flying off, hitting 9 other nuclei, and so on and so on. And this is called a nuclear chain reaction, and it gets out of control. So this is what it looks like. Our neutron hits, you get a little bang as the energy is released. Now remember, every time a nucleus splits, some energy is released, and then we get another collision with these three, and you get a slightly bigger bang, and more high energy neutrons released, and they collide with another bunch, and you get an even bigger bang, and this carries on and on and on until you get an extremely big bang, which is a nuclear bomb, which you've all seen. After about 30 cycles, you will have had the energy from 68,000 billion atoms. So you've got some appreciation of why these things are so devastating. So how does this work in a nuclear power station? Why doesn't a nuclear power station just go into meltdown? Why doesn't it just explode? Why don't you get a nuclear chain reaction and it goes out of control and the place explodes? Well, the main reason for this is you have this thing called boron, these control rods which are made of an element called boron. Now, boron has got a very special quality. What boron does is it absorbs neutrons. So all these neutrons, which would lead to a chain reaction and a devastating explosion, they're absorbed. And what you can do is you can calm the reaction down by dropping these boron control rods down in between the fuel cells. These fuel cells, these fuel rods, they're uranium. And if you were to take those boron control rods away, or get rid of them completely, you would get a chain reaction, and you would get a nuclear bomb going off. So these boron control rods are really, really super important. And if you had some emergency, it was getting too hot, or you had some terrorist emergency or something like that, all they'd do is there'd be a fail-safe. It would drop these boron control rods down, and all the neutrons would be absorbed, and the reaction would stop. So it's quite a nice way of controlling a chain reaction. So what's the point of all this? Well, the point of it is to generate heat. In a coal, oil or gas burning power station, they burn this stuff and it creates huge heat. Well, that's what this does. That's what the chain reaction does. That's what this fission reaction does. Why do we need to generate heat? Well, the heat causes water to turn into steam. Steam is under huge pressure, and this pressurized steam turns a turbine, which turns a generator and creates electricity. This picture here, this was a power station called Chernobyl, in a place called Chernobyl, and in Russia, and it's melted. It didn't explode like a nuclear bomb. It was a meltdown. For some reason, they pulled the boron control rods up and they switched the water pumps off. So there's no water pumps, no water going through, cooling it down, taking the heat away. The boron control rods weren't in there, so they weren't doing their job, and the thing just got hotter and hotter and hotter. And there's a point that can be reached where you can't go back. You can't just say, oh no, they're too hot, I better chuck some more water in there, because it's too late. And the thing went into meltdown, and you can see the building has just melted. And what was happening was it was throwing nuclear waste up into the air, and this was falling on Chernobyl and surrounding areas, and some of it was going high up in the sky. This thing, although it wasn't an explosion, it did raise the radioactivity of the atmosphere of the whole Earth by a small amount. So this is one of the biggest and most famous nuclear disasters in history. Although saying that, fewer people have died in nuclear accidents than they have in coal-burning power stations. You think about it, where do we get coal from? Well, we mine for it, so tunnels collapsing and the amount of pollution and particulate matter that's caused by coal-burning power stations. In comparison, nuclear power stations are pretty safe. The only problem is you end up with some radioactive material that's going to stay radioactive for a very long time, and we're not really quite sure what to do with it at the moment. So there you are. That's what can happen if things go wrong. So here's a power station. Let's look at it in a little bit more detail. Now, you do need to know this stuff, so you may want to copy this diagram down or write some notes on it. Our reactor there is generating phenomenal heat by a nuclear fission reaction. That is turning water into high pressure steam. The high pressure steam spins a turbine, and that turbine spins 50 times a second. That spins a giant electromagnet around a coil of wire, and that creates electricity. It turns movement energy, kinetic energy, into electrical energy. That electrical energy leaves the power station. It goes through a step-up transformer, which steps the voltage up so the current's not too high, and it works its way down the national grid to our homes. What happened to the steam? That steam that turned the turbine, well, it cools down, it condenses, and it's reused back through, recycled, but it has to be cooled. So you have this cooling tower which passes condensing water through it, and you've all seen these cooling towers with what looks like smoke coming out of them, white smoke. That's just water vapor coming out of those things, those towers. So it's not a problem. There's no pollution issue with those. A nuclear power station, apart from when it's being built or when it's being decommissioned, that is taken down, during its working life, it does not produce carbon dioxide. It does not contribute to global warming. So that's one of the major advantages of a nuclear power station. We've got a picture here of Nagasaki. This is one of the places where the Americans dropped the bomb. This is 3 days before the bomb. This is 2 days afterwards. You can see how destructive these things are. And there's another picture of it there. And a lot of people, who survived this were coming out with terrible burns and radiation burns. And people were dying a long time afterwards of cancer, because a nuclear bomb also gives off gamma rays, and gamma rays are very ionizing, very damaging, especially to biological tissue. So you get DNA mutations, and you get kiddies born after the bomb was dropped, but these kids are born with leukemia, blood cancer, or other kinds of cancer. So the destruction didn't stop on the day that the bombs were dropped. The misery for many carried on. So there's a picture of this bomb, 11 miles high, this cloud of ash and dust that was created. So there we go. Quick look at nuclear fission. So we've covered nuclear fusion and nuclear fission. Don't forget, we've got a link to the GCSE Bite Size page. So do the revision on fusion and fission. Get yourself 10 out of 10 on that test, and then you're ready to move on. We've also got a link to a past paper on the site, so use that as well. Use everything that's on there. There's 4 questions for you to do. Pause the video now, have a go at those, and then have a look at the answers and see how you did. So good luck. Thanks for watching.